So, hello, Gothic and Russia. My name is Yoni. I'm from Israel. Nice to meet you all. And thank you, everyone, for making this happen, even in these kind of days where it's very hard to get anywhere. So I'm currently talking from my house, like everyone else. And in this talk, we're going to talk about wrapping in C++, Arrow. Arrow is an open source package we're going to talk about. And I'm going to discuss why did my partner and I do it and what are we going to do with it. And this talk is going to be divided into three. So first, we're going to talk about motivation. Now, Natalie gave a great background about how does a machine learning pipeline looks like. And there's a lot into this motivation, so we're going to talk about it. Second is going to talk about language binding, which is something that a lot of you probably know, and if not, we're going to say a few words about it. And the third part, we're going to relate it to Go specifically, and the challenges we had in writing this package, and where is this package going. During this talk, I'm going to look sometimes aside. This is mainly to try and see the Q&A in the chat, but I'm not very trained into this, so you'll have to excuse me if I'm going to miss. So if there's an important question, I'm sure that Elena and Alexei can just point me out, and in the end,
yeah, we monitor them. Don't worry.
Yeah, it just translated for me as well. I'm not a Russian speaker. That's quite obvious, and English is also my second language. So I'm going to try and be as clear as I can get. But if there's a question, you can ask. So, a few words about myself. About me, I'm married. I've got one child and 4 dogs. This is why you're going to see a few pictures of my dogs during this lecture. I'm currently a data architect and a software engineer at Bond. So Bond is a startup that works in the personal safety market. And currently we're out in the USA. And like everyone else, changing what we do in these times. Before that, I worked for Sears Israel. So Sears is an American company that did the e-commerce. There I used to do mobile and React Native. And before that, I worked for iSight Mobile. I did a lot of Java and JNI, worked in mobile and SDKs. And before that, I worked in Alvarion, which used to be the Nokia of WiMAX. And today there's no Nokia, no WiMAX, so there's no Alvarion as well, I think. But I used to write embedded code. So what's the motivation? Why do we want to, what are we trying to solve here? So as you saw before, there's a thing we do a lot in software engineering, which is moving data around. So we got all this infrastructure and data is moving. And when data moves, we do something which is very compute intensive. We do a serialization and deserialization. The reason for that is the I/O between the services and the fact that each service is written in a different language. Now, another thing which we do is a lot of data exploration. So those AI pipelines don't build themselves. There's a lot of data scientists, and there's a lot of analytic works going in there. And a few years ago, everything was right. A data scientist could work quite easily on his computer, but the data gets bigger and bigger all the time. And it's not only the fact that you can work on a distributed system, you can also work locally, but you need more and more memory. Now, memory doesn't grow as well as the data. Data just gets bigger. And we need a way of working, even on our own computer, with the same memory limitations we have. But even if we work distributed, we want to be efficient. So we have Apache Arrow. Now, Apache Arrow is a cross-language development. This is from the wiki, of course. Cross-language development platform for in-memory data. It allows you to do zero-copy streaming, messaging, and inter-process communication. And there's a lot of languages already supported, which is C, C++, C#, Go, Java, JavaScript, MATLAB, Python, R, Ruby, and Rust. And of course, you can imagine that the main customers for these are Python, and R. And the reason is because the majority of the AI and analytics is built with Python. But unfortunately, the majority of the big data infrastructure is built with Java. For example, Hadoop and Spark. So Apache Arrow tries to solve it by building a common data layer in memory. So we have all this infrastructure, which is Spark and Pandas and Drill and Impala and CUDA, Cassandra, Parquet. We can just describe many frameworks. Every time we want to move the data between them, we need to copy and convert. We need to do serialization, deserialization, and we probably won't do it that efficiently as well because we prefer the data to move, and we'll just scale it horizontally, so we'll pay. Arrow memory allows us to actually share the memory between the systems, and we'll talk about how it does it. Another advantage is the fact that the memory is stored in memory in columnar pattern. So what's the advantage? If you know Apache Parquet, that's for storage. We store it in columnar, it's much more efficient. So columnar data is much more efficient, you can compress it much better. That means that I can use the same memory layout to store much more data, even on one instance. So I can, for example, load a very big data set into my computer and just work on it without even doing any distributed work. It doesn't sound like very important when we talk about a time, especially when data scientists do a lot of work. Every time they need to move from a non-distributed to distributed, takes a lot of effort, engineering-wise and even computational-wise. Another advantage is that we can do a single instruction multiple data. That means that in columnar data, we can be much more efficient, work multi-threaded, we can have specific hardware that gives us efficiency, and we can also do things which are, for example, filtering the data in the bottom layer. So instead of getting all the data through a third party, for example, an S3 or any distributed storage, and then filter it on the client side, when you work in the columnar when you work in the columnar way, you can just do it in the server itself or in the data itself. Another advantage is the fact that the data is actually stored in the memory continuously, and you can reach each part of the data in an O1 notation. That means that you can read the data very fast, and it's very easy to build cache layers over it, and it's very easy for writing it in other languages because we know where we can get each part of the data, and all we need to do is to pass the schema. So this is an example, for example, how we look at a JSON data. So you can see the data is actually continuously, and the memory layout is efficient. Another very cool and very new feature they have is Apache Arrow Flight. So that's a framework for fast data transport. It allows you through a gRPC and the Arrow memory layout to pass data without serialize and deserialize. This, for example, can allow you to pass data in 2-3 gigabyte a second pipe, and you pretty much reach only the limitations of your network bandwidth. Companies, for example, like Dremio, reviewed it, and they say that it seems to them like the future of JDBC, ODBC, of driver clients, of database drivers. So an example for that would be a Snowflake data warehouse with Arrow. So until now, you could only use a regular, for example, Python client for a driver for the Snowflake. So Snowflake is a big data warehouse. It's actually a combination between a data lake and a data warehouse. You can store as much computation as you would like. And what they did is they implemented using Apache Arrow the driver. So now you can fetch the data 10 and 15 times faster using the same code, but a different driver. So for you as a Panda user, Pandas is a library which you use to work with data in Python. You can just read the data and get it 10 and 50 times faster. You actually also save a lot of money on computation because you pay when the data warehouse is up. And if you do things much faster, then you pay less. So this is not only efficient for the work stream, it's also efficient for saving money. So if we look at what we got, what's the motivation? So we got all the infrastructures, all the third party, all the open source buzzwords on the left. We usually have our own Go service and number cruncher. And it's easy for us using Apache Arrow to get the information fast and reliably into our number cruncher. And in the end, we can also use the flight mechanism to pass the data to another server, which can be, for example, our Python TensorFlow server that does inference. So we can get the data on the left, we can pass it fast, and we can crunch it with our Go service. So who's leading this work? So there's a company actually called Ursa Labs, and it's led by Wes McKinney and Adley Wickham. So Wes is very known for building the Pandas project. And Hadley is known for being an architect for the R language. Now, I didn't ask, but I will ask now. Is anyone in this audience is doing any analytics or data research? You work with data, not only with Go infrastructure. Can we ask this question, Elena?
Yeah, please raise your hands.
Just tell me the number of people raise their hands because I can't see it myself.
So far, no one.
Okay, good. So if you had been working with Python and data, you would know Wes McKinney, right? And what they did is to build the Ursa Lab. So that's a company that pretty much does open source as the main product. And they work on donations and investments from third-party companies, for example, NVIDIA or RStudio. They invest in them to develop that open source project, which is quite an interesting paradigm for a company. And they lead it. So we finished with what is Apache Arrow. So I'll just conclude. We have an in-memory columnar schema and framework that we can reach data very fast, and it can allow us to get data from all sorts of like third parties, for example, databases, data warehouses, files, Parquet files, CSV files, and it can treat everything the same. Now, let's talk about what is a language binding. So a language binding in the context of software is actually a REPL library that allows us to bridge between two programming languages. This is very known if you've been working, for example, with JNI. So JNI is a Java native interface. It allows us to read code from C and C++ using Java, use shared libraries. Very well used in big data and in Android, for example. Another good example is Python. And we got also that in Go, and we'll talk about it specifically soon. So where do we find this language bindings? We find it a lot in TensorFlow. So TensorFlow is written in C++, and yet the main usage is in Python. How do you do it? You use, for example, a library called Cython that allows you to write a binding between C++ and Python. Another good example for that is NumPy. So Python is a single-threaded language, yet NumPy works multi-threaded. The way it does it is that the code is written in C++, and you only orchestrate the code in Python. Another nice example that I've been using a lot is React Native in my past. React Native is a library that allows you to write one time the code, for example, in JavaScript, but you actually work with native code in Android and iOS. The way you do it is by having a very strong language binding and an engine in behind. A nice example of it being used in Go is the Kafka library. So Kafka is a log provider, we all know, and it's written in Scala. but a lot of languages got bindings for it. So you can you can bind for it in Python and JavaScript and Java and even Go. So how you do it, you actually install a library called librkafka. And we got a code in Go that links to it. And this part is actually where you see, if you go into the Kafka edit.go, you see this part of code, and we'll talk about it, that this is a C code. So it actually needs to know the symbols, and this is how they link the Kafka, and that's where the things go together. There's also a very good implementation, by the way, for the Go client for the Kafka client in Go, but this is the one they have in Kafka. So Apache Arrow, the project, it's got also language binding. So what's the status? So they've got native implementations in Java, C++, JavaScript, and Go. Now the Go one was built by the team that built InfluxDB. But it's not always maintained. It's actually been kind of left alone for the last few months, looking at the GitHub repo. You also get in JavaScript and in Java. So the way you do it is they actually implement the spec. Not fully, but they implement the majority of it. Of course, in Java, they do the majority because it's a big data ecosystem. And what they do in C++ is you got, first of all, somebody who built a C bindings of a C++. And you use that actually to get the Ruby. So you can add Ruby over the C bindings. And we'll talk soon why you have to have those C bindings in the middle. Another big ecosystem user is Python, as we said, because the person who invented it is actually inventing pandas as well. And Panda is a big user of Arrow. And we do it in Python. So how we do it, we use a thing called Cython. So the Apache Arrow Python binding is based on the C++ project and is built with Cython. So Cython allows you to write this middle code between C++ and Python. It's sort of a weird language, not the nicest thing in the world. You get kind of like the worst of everything, the worst of C++ and the worst in Python, but it's a very easy way of making bindings. And that's a very hard problem in software engineering. We'll talk about it soon in our context. So this allows pandas to be integrated to Arrow, and you have, for example, Parquet reader and CSV readers, which work very fast. You can reach S3 storage using that, and you can actually have a common layer between all those and have like a single interface to them. So you can interface, you can reach your S3 and your files and a local file system and remote server and a database, everything is the Arrow binding, and you can have like a single layer of control, and pandas just reach it, and it's considerably efficient. So a possible awesome usage we want to do in our context of Go, we would like to share a table with Python in the same memory space without serialization. So we would like, for example, to be able to have some code running in Python and in Go on the same process and share data between those two without any serialization. Another feature, which is very nice, we would like to do is sharing the same data between services without serialization. So this is something we can do with Flight. So what options do we have when we want to do this in Go? So the first option, of course, which is already done, is to implement the spec in pure Go. What's the advantage of doing it in pure Go? First of all, it's a closed problem, right? We've got the spec, so we know what we need to implement. We write all this bunch of unit tests, and we go for it and just, we just write it down. Go is the language as Go developers that we feel comfortable with. So it's, the better I am at implementing it, the better I can do it, right? It's kind of easy if you think about it. And the advantages as well are that you get all the whatever Arrow can give me. So if I read the spec today and I work it today and I can finish it, for example, tomorrow, then everything that Arrow supports I've got. It's in the spec. Plus, in Go, we can pretty much improve the implementation. So concurrency is very hard in C++. In Go, it's easier. So we can do all sorts of things much faster, much better. But what are the cons? So it's very hard to follow the changes. So when you got new and very complicated features, for example, the flight mechanism, it's very hard for a Go developer to go into the C++ code and the architecture code, understand what happens there, implement the entire interface from scratch, and then have an integration test that makes sure that everything works and doesn't break. If that's the case, it's also harder to maintain, because for have a good maintainability, I need to automate a very high level of the spec and make sure that every time a version goes up, I can do that. And another thing which makes it a bit unpopular is very hard to give back the improvements back to the C++ main project. So if the main project, the main branch is built in C++, they won't want to have implementations in pure Go. We would prefer having things that are based on their C++ implementations. And without that, it's very hard, because if I implement everything in pure, they need to make sure that it doesn't break anything else. If we look, for example, on the number of bug fixes in the latest version, we can see something which is very crucial for success of an open source project. So you can see that the majority of the improvements were done in C++. And when we say that the improvements were done in C++, what we can also see that the second language that had improvements was Python. Now, the Python framework also enjoys from all the C++ improvements. That means if I'm a Python developer and I work with Arrow, I enjoy all of these improvements in my ecosystem in bringing a version. But if I'm a Go developer, I enjoy this small subset, about 1/7 of the features. And that's not great, not great at all. That means that not only it's hard for me to maintain this project, it's also hard for me to keep up with all the new features, because the first thing I have to do is bug fixes and then get all the new features. So this is a very bad way of for a project to maintain itself. So what was the solution that we decided to do? So it's me and my friend around Miki. Miki actually runs the GopherCon conferences in Israel. We had one 2 months ago, and actually Dave was in Israel months ago, and Natalie was in our conference last year. So it's good to see you all. And we decided to build Arrow, which is a Go bindings over the C++ API. And we want to discuss why did we do it, the pros and cons against it. And the reason I had time to do it is because I live in the suburbs. So I didn't say, but my day-to-day work, I actually write mostly in Kotlin and Python and JavaScript, TypeScript. I'm a data architect, but I'm also a generalist in the company. But I have a long train ride to work. And now, for example, when we all work from home, this is great for me. But when I had to go to work every day, I felt like I needed something to pass the time. So I decided that I'll invest this time in this open source project. And this is, you know, it's a bit every day, but it sums up to a lot after a while. So what's the advantage of binding Apache Arrow in C++? Just a sec, I'll let my dogs relax. Okay, good. So the advantage is that the project enjoys all the C++ main project improvements. The advantages are that, for example, every time we want to upgrade a version, all we need to do is just get the new C++ bindings. And when we get the new C++ bindings, we get all the improvements from the C++ project. I'll show you soon how we do it. Another improvement is that we create some additional features in Go. We can bring them back, okay? We can bring them back to the project. So now it's not part of the Apache project, but soon it will. And then we can just bring it back. And I mean, I hope it will. And then we can, some basic implementations, for example, a CSV reader or an S3 reader that we can enjoy the concurrency, we will be able to bring back to the main project. So what's the cons are? The cons are that it's much harder. much harder. And then now we're going to discuss why it's much harder. So challenge number one, and now we're back in Go. Challenge number one, Go in C++, just they don't link. What does it mean? C++ compilers, they do symbols mangling. Why do they do symbols mangling? Because in order to support linking, the linking is based on C symbols. And C++ got all these new features, for example, namespaces and monomorphization and template functions. And the linkers don't know what does it mean. So C++ got to do this memory mangling in order to support it. Unfortunately, CGO, and it's not only Go, majority of languages don't support linking to C++. CGO doesn't support it. Therefore, you need a C wrapper. Now, we looked at the C wrapper that we spoke before for the Ruby project, but we wanted something that is more directed to our Go project. So how does it look? And what do you do in that case? You do this simple trick where you wrap the C++ code with a header that gives C symbols. So you say, if there's C++, you extend C. That extends non-mingled symbols. This allows us to write this C functions that actually work on the C++ code, but they export C headers so we can link them with Go. Another challenge in this is building a C++ Go project. So the ecosystem is quite cumbersome. That's why is it so big? So the C++ libs and headers are required because we are building a binding of another language. That means we need to have a very sophisticated dev environment, which is more complex than a regular code project. And even there's a lot of complaints in the Go community about the ecosystem of a Go project, or at least they used to be, now it's much better. In C++, it's worse. And when I say worse, you have to believe me that if you haven't experienced the C++ project maintenance, then you can feel very lucky. Now, the solution for that is actually using a Docker file. So we use a Docker file, and we write a lot of our code in the Docker file as well. So I'm going to show you, it's got a C++, the bindings. It's got also Python, because as we said, we want to do integration tests with the Python as well, so we know that we can cross the languages without a problem. And we got also Go there. So how does it look? The general Docker file is quite simple. We use this is like the highly simplified version. So work in Ubuntu, and we need GDB and all these tools. GDB is right. We need to compile native code, and we also need Go. And then we also get all the Python binding. So we can also check the code when we can actually communicate between Python and Go libraries, Python and Go code using Arrow. So we install Miniconda, and then we install Python as well. So we do a bit of experiments there. And the lovely part is this. So this is how we choose the version of our Arrow library. And as you can see here, it's 0.14. Now it's actually already in 0.16 in our source code. And except for a few minor changes they did in the API that we needed to fix, there wasn't a lot. Between 14 and 15, it was just pretty much putting the number up. And this is a great win for using bindings of implementing it yourself. Another challenge is the fact that this library, it's got a lot of types. So as we said, it actually defines in-memory data frame, okay? So it means it's got to support many, many types. Now, this is great in many languages that support, for example, generics, okay? Generics is very useful when you work with this kind of libraries. Unfortunately, in Go, we don't have generics. Unfortunately, depends on your art. So the way you do it usually in Go, in many other libraries, is using templating. And you use templating in order to generate code. So how does it look? This is a small example of the generated code. So for example, I've got many arrow types, and that's the only place where I change or add code in similar types. And then we write a template and we generate it, right? So code generation is, first of all, very fast, and second of all, is quite a sophisticated, let's call it a template language that you can use to write a lot of the code. This allows me to write, for example, just once this logic and then enjoy it for all these types. Another advantage is, well, another disadvantage in doing this is not all types are together, are the same. So a timestamp is not the same as a Boolean. That means that in order to build a very useful template, we need to have the wrapper code between the C++ and C be very, very tailored for our needs. This is why it's quite comfortable doing it the way we do. Challenge 4 is log. So how do you log everything? In Go, the way you log everything is usually, you can use a Go logger, right? But what do you do in the C++ code? How do we serve best our users of this library? And when we say users of this library, we have two. We have developers, other developers. How do they know what doesn't work when they write? Or what happens if the bugs that happen in using this library happen down the pipe in the C++ layer? And then we have the people who are in the Go layers. So when you use this language, when you use this library, and when you build some service that uses it and you get an error, you would want your errors to look the same, so it's easy for you to work with this. And the challenges are between having the logger in Go only and then bringing down the pipe to C++ code, or having a separate C++ logger and a separate Go logger, or even doing something weird, which is having a C++ logger and bring it up the pipe. It's probably not going to happen, but these are the challenges you have. Currently, what we do is we bring all the errors up the stream to the Go and we log them in. And then error handling, the same. So in Go, when you write Go language, you usually have the paradigm of returning a value and an error, right? If you work, for example, with a map, you do some sort of, you get a value and okay. Or if you work with any other function, you get a value and an error. But in C++, that's not the case. Now, the question is, do we want to build a code which is a C++ mindset in the C++ and a Go mindset in the Go? Or maybe we want to try and apply our Go mindset into the C++ code. So that's what we chose for now. So what we do is we usually return from our functions, from our layer, a struct. And that struct's got a value and an error. And this allows us to have the same paradigm we use in Go, actually in the C++ layer. And it allows us to, well, float everything up to the Go and log it in. A big challenge, right? No, there's a reason why I call it 6-6. A big challenge when you work between two languages is memory management. So let's have a discussion about memory management. So the Go runtime, we all know and love. It's garbage collected, and it's quite efficient, it's quite fast. C++ doesn't have memory, doesn't have garbage collection, but Apache Arrow is a very modern library. So they use two things extensively. One is a shared pointer and the other one is a unique pointer. Now, shared pointer and unique pointers are a C++ feature that allows us to have a sort of a reference counter. And well, this works very similar to a garbage collection, that when there's a zero reference counting, they actually release the memory. Now, this would have been great if we've been working in Python or in Go or in C++, but unfortunately, we write in Go. And in Go, there's a different memory runtime. So how do we make them work? In Go, we want to make sure that the memory, the pointers we go to in C++ are predictable, that they don't disappear under the hood. So what we do, which looks quite simple, but works very well, it took us quite a while to understand, is to actually wrap those shared pointers with a struct. And that struct has a regular pointer, which is predictable for us. Now, why do we want this predictable pointer? Because as long as our pointer, the predictable one, points the shared pointer, we know that the C++ runtime is not going to free that memory. But still, we need to free that memory somehow. So we do, again, another thing which you usually don't do in regular code, and we add a finalizer. Now, the finalizer is a code that runs when garbage collection wants to free the memory of a Go struct or Go memory. Now, this is usually considered a bad practice in Go. But when you write a library like we do, this is actually the only viable way of doing this. So what you actually do is you wrap every shared pointer, as we said, with your own pointer. And you have a function that, for example, a schema free, that allows us to free that pointer. Now, when we are done with the Go memory, the set finalizer is called, and it deletes our own pointer in the C++ runtime. What happens then is that the counters go down to 0, and then the C++ code, the runtime, frees the memory. So what we are actually doing here is just having our own check that we need to manage on the C++ memory. So it adds the complexity of managing that memory, but it works. Another challenge is what we call FFI, a foreign function interface. So a foreign function interface is a mechanism which a program written in one programming language can call routine of another language. Now, I brought this example from this package, FFI override, that shows how much override you have when you call a simple function from C, right? In C from other languages. And what we see is this is the time in nanosecond, the time in milliseconds, but we see that Go takes approximately 32 times more to call the same C function. That means there's a significant overhead in calling a C code from Go. So it's not going to be that simple just to wrap everything between Go and C. In order to keep it efficient, we actually need to make sure that we also don't call all the time the C code. So how do you deal with it? A very easy and efficient way to deal with it is using a builder pattern, for example. So when you want to write an array, you do it in the Go layer, and only when you're done, you call a finish function, which calls a one batch operation to the C runtime, C++ runtime. So instead of making instead of making many requests to the C level, to the C++ runtime, we do only one. And this pattern, for example, in this example, we have about 7 times faster. Another challenge, which we're now going into already developers world, is making the package Go gettable. So let's think about how this package is built. So this package is written in C, right, over C++. It's our layer and another Go layer. Now, the experience the developer would like to have is just to go get and to start work with the library. You wouldn't want to set up the infrastructure too much. You wouldn't want to start doing all sorts of like weird hacks or to build using Mac files, all sorts of C++ code in order to work in Go. This will make this library unusable. And when you work with, and of course, when you compile things natively, you also have the architecture as part of the challenge. So when you, for example, if you compile Go code in a Mac or in a Linux, it's not the same compilation, right? So it's not Java. We don't have a VM that helps us keep the code together. So how do we precompile for each operating system? And how do we make sure that people can use this? So first of all, you add a README. You can't run away from that. And you do have some assumptions that the person that want to use it has some experience, at least with Pyro. So he knows the ecosystem a bit. But we still have the problem where we need to pass you, we need to give the Go user a shared object. Right? We need to give him a library that is compiled, that the Go is compiled to it and can run with it. So all you need to do is just import your Go code and start working. And then this library needs to know to link to the correct bindings for the correct language. So how do we do that? We do something which you can see in many other packages that have the same challenges. You actually precompile the artifact in a few architectures, and you bring it up to GitHub. You put it in the Git repo. And then you have, for example, in our case, we have a library called bindings, and it's got precompiled artifacts in all sorts of operating systems. And here we got, for example, the Linux one. But still, the Go code is one. So how do you make sure that the Go code compiles to the right library, right? We can have, for example, bindings Linux and bindings Darwin, which is the Mac. But how do we make sure that it binds to the right library? That's how you do it. You got the Cgo Linux. You got this thing that tells you what is the operating system you use, what the architecture. And for example, I say to the Go code, if you see a Linux, if you're in Linux, you link to the Linux shared object. But if I would want to add also for Darwin, then I'll add the second line that says Cgo Darwin LD flags and go to Darwin. Now this is very important because it means that the library can have many flags which are shared, but it will only link for the correct architecture library. So this is quite, this is actually written in the documentation. Now Cgo, which we use extensively here, is not the most user-friendly feature of Go to date. So this is just so you can understand, this is Go code, and you actually write this code as a comment, right? And this is read and being run on runtime. So it's quite weird, but it works. It works very well. And if you ever go into this world of using bindings and Go and see, that you'll notice that, well, the documentation is quite comprehensive, it's quite good, but it's got its quirks. So where's this package now? What's the status? So the status now is we're adding more features. The features are mostly data types. We got a few data types that are harder than the normal ones, and we want to make the code cleaner and cleaner. And we want to add some good use cases, which is usually the flight. So I'm currently working on adding the flight mechanism, that inter-process communication between services, which is very fast. And hopefully this feature will add a strong use case to using Go and Apache Arrow together. And after we do that, we would like to add the project to the main Apache Arrow repo, and that will give us a bit more, more of a community-driven approach to supporting this package. Any questions?
Thank you. There is one question right now. So the question is, you've wrapped Go code in C code, then wrap it in C++ code, and finally send to Arrow. Doesn't it produce big overheads than just unserializing and serializing data?
Okay, so this is a good question. So let's think about it. What is the purpose of a very good library? A very good library possesses a lot of the complexity, but provides a simple API for a developer or a user, right? To the user, which in our case is another developer. So you're right, this library contains a lot of complexity, finalizers and C and C++, and memory management and templating. There's a lot of complexity inside. But what we gain is a simple Go API that can support all the features in Apache Arrow. And we gain the fact that we are not copy-pasting the schema and have mistakes there in implementations, but we actually use the original C++ implementations for each feature, and we just use Go to orchestrate the usage of it, okay? And that's the goal, right? So we embrace this complexity, but hopefully we'll be able to expose simplicity. Unless, the other way is having a lot of, not having a very complex library, but make the life of the user, the developer, harder. Okay.
Oops, sorry. Any other questions? Just remind that we still have prizes for the best question. How did you test the results in library, especially the C++ part?
Okay, so we actually, okay. So how do we do it? We got in the Docker file, as you can see, we have Python and we have C++ and we have Go. And what we actually did is we built some test cases where we run in the same memory space the Go code, the C++, and the Python. And I built an end-to-end package that calls from Go from Python, goes through the Go code, creates a table, and then reads that into the memory and presents it. So we write end-to-end tests currently in memory, and it's quite hard because we needed to use Cython in order to have that layer between Python, Go, and C++, but we did it. And the next layer, which we're going to do with Flight, is going to be simpler, because what I'm going to do is I'm going to take the same examples that they use in Python for Flight. So they take like this huge CSV and they pass it between two services. And I'm going to do it in Go. So it's going to be like a Python service and a Go service communicate and pass data in a very efficient manner. And yes, it's complex, but once you get over the hard is always the beginning, like getting this API. Once the APIs are written well, it's very easy because it becomes like regular either Python code or Go code. It's quite easy to use.
Okay, there's another question in chat. Can you please open the slide with problem number 5, just before problem number 666? Challenge 5. Yeah. So the question is why you need the third parameter? I guess I. Why you need I there?
Okay, so we have the pointer and we have the arrow. Oh, sometimes we pass the size. We need to know the size because we pass here like pointers, and it's very easy to reach to allocate memory, which you don't. So you usually pass the size as well.
Okay, the last question that we have now: Do I need a C++ compiler to use the C Arrow library in Go?
Do I do what?
Do you need a C++ compiler?
Ah, okay. So the point, yeah, you do need a C++ compiler, right? Because what we do is we write the C wrapper around the C++. So for that we need So we write the C++ and then we use the Go code as well. Let me think about it. Yeah, we need to for the compilation. No, we actually compile with the native Go compiler. Yeah, no, we can manage. Once you work with it, yeah, you won't need any C++ compiler.
Yeah. Okay, that's the last question we have.